Well, thank you very much. As John kind of noticed last time when I wrote down my title, More Chromatic Homotopy Theory, you could read that both as more chromatic homotopy theory or more chromatic homotopy theory. And indeed, we will continue being able to see that in two ways, because let's say, in general, we have the spectra En, of which we can, which we can talk about mostly by considering their homotopy groups. So, always good to just write them down again to make sure you all remember. And we'll have our K theories, Kn with these coefficient rings. And then last time we mostly looked at what happens at n equals 0 and n equals 1, and a little bit about what people can do at n equals 2. So we saw that at level 0, everything is rooted in just rational homotopy theory. And that E1 and K1 are related to topological K theory in the sense that localization with respect to E1 is the same as localizing at P local complex or real topological K theory. And localizing with respect to K1 is the same as K localization P completed. So we talked about that in detail last time. And I also said a little bit about what you can do at n equals 2. So n equals 2 was related to so-called elliptic cohomology theories. And people also like to spend their lives doing calculations, trying to calculate some homotopy groups of K2 local spheres, for example. But, I mean, this whole machinery, it seems a bit overkill to just define all that and go through all that work to just say, we now have a really pretentious way to talk about K theory. There has to be more use to it than that. So today I would just like to wrap it all up by telling mostly a story about how for general ends we could really use those to really get towards our goal to study the P local stable homotopy category. And I will list results without necessarily saying how they will be proved, because of course I could just say, oh, I'm picking one theorem for my lecture series and I'm going to prove all the lemmas in great boringness, but I think it would be nicer to have an overview of the main results. So first of all, I've always said all the time, this one is the kind of nice one and sweet one that behaves more like P localization, and that one behaves more like completion, which even the expert said doesn't always behave as it should. So, but of course, this one also has its uses, so let's just talk about some of them. So the first thing, where is this one? Let's put it a bit higher up. So the first thing to say about En is that by work of Ravenel, and it occupies huge chunks of his orange book, that localization with respect to En, which you remember we just wrote as Ln, is smashing. Which means, to just remind ourselves, that Ln of x or you localize by smashing with a local sphere, just like P localization. However, LKN is not. So while this one, as I said, occupies several chapters of Ravenel's Orange book, this one, if you believe me that the following exists, is not so hard. So assume that there is a spectrum with the following properties. So E should be Kn local, but not rationally trivial. Let's just assume that such a thing existed. Then, okay, so we have that, well, I'm just writing it down again. If E was Kn local, then I could just replace E with its Kn localization because I wouldn't change anything. And if I assume that if Kn was smashing, then I can replace E with E smash the Kn local sphere and it wouldn't change anything. And I still have to carry that HQ around. And now, if we just look at these two together, that's actually trivial. So there are lots of really nice papers that look at the interaction of localizing with respect to Allenberg-MacLane spectra, which that one is, and other homology theories. And well, that one would be trivial. So the whole thing would be trivial, which of course would be a contradiction. So if we have such an E, then we could show that Kn localization is not smashing. Thank goodness there is such an E. Anybody know what it is? Just by any chance? Neil does, is Neil here? He's probably writing lots of slides. So we could take the Morava E series, or rather the nth Morava E theory En. So you don't have to know what that is, but it exists and it has those properties. Okay, but we don't just want to say this one is always so nice and sweet and this one is just horrible. As a parent of two children, I know that this attitude would run into great problems eventually. So let's say something nice about Kn as well. So Kn, and we will actually need that later. So it has a Knuth isomorphism, namely that if you want to know what that is, then it indeed decomposes as a product of the two respective cohomology rings. And not just that, you might say, maybe they all do that, but in fact, there is some classification theorem. I really don't know that very well. That to have a Knuth isomorphism, it either has to be this or singular homology. So that makes it kind of special. And as a consequence of this kind of, no, not quite. So another nice thing about Kn is, last time I gave that lecture series, I had the impression that Kn came off really badly. And now I just think I say lots of nice things about it and nothing about that. So Kn is a graded field. What does that mean for a spectrum? It seems like a weird thing to say. Well, as we've all known since we were teenagers, every module over a field is free. And this is also true here in the sense that every Kn module spectrum is a sum of shifted copies of Kn itself. So, and therefore, as a consequence of this, we get that if we take the homotopy category of Kn module spectra, so that's a ring spectrum, so I can look at modules over that ring spectrum, can put a model structure on that, and then I get, I can form a homotopy category. I can just apply homotopy groups and get into the derived category of graded Kn star modules. So that's just a graded ring, and I can look at its derived category. And that is indeed a triangulated equivalence. So this thing, which is something topological, at least in my sense of being topological, even though several of you have said, why is that still topology? So that is something topological, that is something algebraic, and there is a triangulated equivalence between them, and I think it's even a TT equivalence, a monoidal one as well. And why is that an equivalence? Yeah, because in each case you can just count generators. And that is especially interesting because it is a TT equivalence which does not come from an underlying Quillen functor of model categories. You know, if you have a Quillen functor of model categories, so functor that respects cofibrations and so on in a sufficient way, that induces you functor on these guys. However, the converse is not necessarily true. Here you have an equivalence of the homotopy categories, which does not come from any underlying Quillen functor on the model categories. How can we see that it doesn't? Well, I said to you that that Quillen functors do not just induce that, but also equivalences of all kinds of other structures one could make with model categories. And in this case, it doesn't. For example, here, all mapping objects are modules over Eilenberg-MacLane spaces / chain complexes, and here they just aren't. So homotopically, they're very, very differently behaved, even though just the homotopy categories look the same. And another good thing about Kn, something that Neil has kind of mentioned already in his first talk. So this, I would say, is down to Hopkins and Smith. You see, when I first started giving talks about stuff like that, it was still kind of borderline whether that was allowed to be considered classical. And now probably it definitely is. So let's look at nilpotence and periodicity. So nilpotence in the context of stable homotopy theory, if you do stable or even unstable homotopy theory, one likes to look at homotopy groups of spheres, and definitely a classical result is that every element in the ring of stable homotopy groups of spheres is nilpotent, outside of degree 0. So anything that's what makes that ring so hard to compute, because whenever you think you see a pattern and you think, huzzah, that means I know some elements in an arbitrary homotopy group, that pattern will always die because of nilpotence. So it therefore becomes a reasonable question: does everything in stable homotopy always die? Which makes it quite the off branch of topology. Well, but it doesn't. So the KNs detect nilpotence in the following way. So you could either ask for a map to be smash nilpotent, as in if you just take lots of smashed product, that map with itself lots of times. But one would really like to talk about just nilpotence. So let's leave that out, nobody cares about that. So let's just do nilpotence. So a map of spectra will do I really want X to Y, or do I want X to be a self map? It can only be nilpotent if it's a self map. So I can, of course, compose that map with itself forever and ever and never, and then ask myself, will that eventually be 0 or not? Yeah. So that is true if and only if it induces the 0 map just done once in K theory for which one do I have to take? Just all n greater than 0. So one could detect nilpotency by just applying Kn to it. And I also learned the hard way how useful that is. I mean, given the fact that I still talk about that 17 years later, just shows how bitter I am. That was the last little thing I needed to show to make my thesis work, that some element was nilpotent. And I just tried and I tried and I tried and I tried, and it took me like half a year. It felt long. I don't know how long it was. It was definitely several months. It really took me to the absolute brink of my persistence and will to live. And well, you know what it's like. You think you start your thesis and your whole future depends on whether that thesis succeeds, and then you run into that last little lemma that doesn't work. And you know just logically that if that lemma doesn't work, the entire work, which at that point, because you're young, is your life's work, could just unravel. When you grow old and cynical and thick-skinned, you know that even if that's not true, then something else will always be true. But back then, it feels a lot more extreme. And I asked someone, do you see any reason why that map is nilpotent? And he said no. And after I had submitted my thesis, and kind of very inelegantly went around that problem, he said, oh, you could just apply K1 to it and then it's 0. Yeah. Over beers, I might reveal names. Yeah, there was an element of degree 8, which I wanted to be nilpotent, and I could only then prove it by some ancient paper for its square, which had degree 16, so I had to change all my calculations. And then it felt like baking a cake, dropping the cake, putting the cake back on the table, covering it with icing and hoping nobody notices. But thank goodness nobody actually reads the thesis. People read the paper that comes out of a thesis, and in the thesis I could just apply that K1 of it is 0 and made it very short and neat. So there you go. Very useful theorem, that. But you could also ask, are there maps that never die? And these are the ones that Neil has introduced already. So if we take n to be the largest, well, the largest n, that's a stupid thing to say, largest integer, let's say, such that, which way around is it? If we take n to be the largest integer such that this one is 0, for all, that is what I want to say, is it, yeah. So you can ask, is k not 0, is k1 0, is k2 0, and so on. At some point it will not be, but up to then it will be. And once you have identified what that then is, then it's also, I think, down kind of simultaneously to Ravenel's red book, in which this one has just a gap in the proof, and the Hopkins-Smith paper that X has a VN self map. So some power of Vn, don't know what that is, and that one will just be obviously k times degree of Vn. A Vn self map, which means that it is a map that induces multiplication with the power of Vn on the Kn star homology of X. And as that is an isomorphism, in particular, that means that this map can never die. And we've already seen the V1 self map on the mod P Moore spectrum. But one can generalize that. And as I said, and I should also say that's for any m greater than n, this one is 0. So it just speaks to the Kn and of none of the others. And it is a big business to find out what precisely is the smallest one you can find. And what does that even mean? Okay, so now we actually know a lot of nice things about Kn and one nice thing about En. So we could keep on listing, but let's just bring this back together. So one theorem, also very, very computational, due to Ravenel, is the following. And when I say computational, it means involves at least one spectral sequence, and usually more spectral sequences to find out the pages of that spectral sequence. Localizing with respect to En is the same as localizing at the wedge of the Ki's up to Kn. That does not mean at all that En equals that, but you can have the same localization functor even though the homology theories themselves are not exactly the same. Because there was this quite big business, I guess also still around the 90s, of Bausfield classes. So if that happened, if you had two homology theories with the same localization functor, you would say they have the same Bell's-field class. And it was quite big business to work out what the Bell's-field classes of all these homology theories involved are, and also what the lattice of Bell's-field classes altogether, what kind of structure that has, and so on. So that came around that. But as a nice consequence of that is, several nice consequences. If you look at that and you compare En+1 localization and En localization, well, you can already see the following. If X is En+1 acyclic, then it is also En acyclic. Just from that, I mean, plug it in, and then you see. And therefore, because of these implications, almost you could say duality between local objects and acyclic objects, you can therefore say that an X is En local, or if an X is En local, then it is also En+1 local. And that is why I took the time last time to show you that if X was rational, it was K local, because the higher, even more chromatic levels behave just like that. So that means in particular, you have a natural transformation between localization functors, between this one and this one. Fine. And you also have, well, you can write down something similar. If X is En acyclic, it is also Kn acyclic. And you have a natural transformation from Ln to Lkn. So I do not just have a bunch of ENs and a bunch of KNs, and the ENs don't speak to the KNs, and the Ns don't speak to the Ms. They are actually all related. But I mean, just having an arrow doesn't really, I mean, that's not much yet. Because even though if we imagine the stable homotopy category to be big and complicated, let's say it's as big as this board here, I could still just be talking about this tiny little corner here. And if I want to study all of this, it doesn't help me if all my localizations just live down here. I want to talk about all of it. And that is really where I think the absolute jewel in the crown of chromatic homotopy theory comes in. I mean, there's many jewels, but one of the best, the chromatic convergence theorem. So good that it will now need a new piece of chalk. So if I take X to be a finite PW spectrum, still P local, I'm still assuming that everything I do is P local, then X is weakly equivalent to the homotopy limit of applying all the En localizations to my X, getting a tower from these natural transformations, and then I can take the homotopy limit of that. And there. Yeah, let's look at that for a second and appreciate it. So what does that mean? It means exactly what I try to motivate, namely that what? Yeah, I said everything is p-local. Maybe I should write that up. No, I'm not allowed to write up there. Everything is p-local, has been for days. So that means, first of all, you could view this as for increasing n, En localization provides a better and better approximation of the entire stable homotopy category, which means that if I look at En localizations, all of them, I am not just talking about here, I'm really talking about everything I want to talk about. So the ENs are definitely a good collection of localizations that let me study the entirety of the stable homotopy category. I mean, however, one has to, so finite is really necessary. I mean, you could say a lot of important, and not just nice, but important structural things by restricting yourself to compact objects. And in this case, it is really necessary, because if I took an Naolekar-MacLane spectrum, which is not finite, everybody who has ever tried to build an Naolekar-MacLane space will know that you normally need, or you need infinitely many cells to kill all your homotopy, and it's the same for spectra. Then if I plug that into there, I would have Hg, and here I would put the homotopy limit of my lns of Hg, and if we refer again to chromatic localizations of Naolekar-MacLane spectra, I would just get that. And not every Hg equals HQ. So you see that finiteness is really a necessary thing for this to work, because for infinite x, for general x, in general, it just doesn't. But this theorem there also has another really good consequence. Oh, I still have space. Don't worry, I won't go all the way. So in general, you can show that for certain E's and F's, you get a pullback. Which way around do I want to do it? So that could be a lemma, maybe for a discussion group, but I don't think you will really want to. So if you have such a situation, then we get a pullback. And so what are these maps here? Here, this is just E-localization. So you take a something and E-localize it. And here, you, is it the right way around? Yes. What do I have here? Here, that's not good localization, notation. So here you take this and you E-localize it, and there you F-localized and applied LE to the entire bottom row. So it is not a symmetric situation. You cannot just swap these two legs around and get the same thing. So here you E-localize, and here you apply E-localization to the F localization. And you could apply this to this situation here and get the so-called chromatic square. Oh God, no, I'm using all of this. Try and write nice and big. So here you then get ln of x because you pick, well, you see what I pick when you pick e to be en minus 1 and f to be kn. And here you get the absolute horror that is ln minus 1 of lkn. But so you have a pullback square like so, but even if you don't really want to know why this is an absolute horror, it at least morally tells you, just as this does and this does over there, that the kn localizations kind of form the difference between the en localization and the en minus 1 localization. So here you have your chromatic tower, and the difference between the different floors of that tower are the kn localizations. So that just shows very strongly how just the ENs and the KNs, they really live and work together. And that then brings us to probably what some people in the room would consider even better than the chromatic convergence theorem, namely the thick subcategory theorem. Also, I think in its initial version down also to Ravenel's Orange book and the Hopkins and Smith paper, you could, of course, ask, you know all about thick subcategories, thank goodness. You could ask, so what are the thick subcategories of the p-local stable homotopy category? Because we really have to say of the compact objects of the stable homotopy category, because just as in the algebra world, you have to restrict yourself to perfect complexes. Here we have to restrict ourselves to compact things. So the non-trivial thick subcategories of the compact objects in the P local stable homotopy category are, so they are exactly the Kn acyclics for varying n. Ta-da. Well, that kind of now seems a bit disjointed from all the other stuff I've been talking about. But I don't know, traditionally that's an n and that's an n minus 1. I'm sorry, but that's how it is. Yes. I assumed that. If I saw that, I would complain about the index, but yeah. No, thank you, sorry. So why is that important rather than just something else? Well, this tells you that this context of ENs and KNs is actually the only way to do with a stable homotopy category what we've just done. So maybe there would be some other family of homology theories with which you can cover the entire thing, approximate the entire thing. I'm just too scared to use the word stratify. Maybe there are other ways of doing all of these things, but that fixed subcategory theorem tells you there isn't. That is the correct way to talk about the stable homotopy category. And well, if you've seen like Henning's and Shrikant's talks, then and Natalia's, absolutely Natalia's, everyone's. Now, once you've seen that, you're only just a little step away from talking about the Balmer spectrum. Because if you look at, I'm not going to erase what I was saying. If you look at the KN acyclics, that's not just a fixed subcategory, but it is in fact a thick tensor-triangulated ideal. Because of this, if X smash Y is acyclic, no, if one of these is acyclic, then so is the product. And actually, because of precisely what's written underneath, which I also haven't erased yet, these are not just TT ideals, but they're prime ideals. Is it a TT prime ideal or prime TT ideal? I just make an arrow and say prime, so there you go. So therefore, we can write down the Balmer spectrum of this big and horrendous, as you see, complicated thing, which I said contains a lot of interesting math and so on. But in fact, now we can just draw it. So here you have a dot belonging to Q, and then for each prime, you just get a string of things. So here you have A1, A2, A3, and so on. And I draw an arrow from, well, a vertex from one to the other. If one is included in the other. So now, this is now kind of the current way to talk about the stable homotopy category and really embed it into this general context of local duality and so on. Which leads me to what I kind of wanted the final chapter to be, just do a bit of a survey of what some of the things that people are doing with chromatic homotopy theory now. So one doesn't just have to look at this. One could look at the Balmer spectrum of variants of this and try and draw it. So Natalia has been talking about equivariant stable homotopy theory. She introduced equivariant cohomology theories, which give you equivariant spectra, which live in the equivariant stable homotopy category. So if I fix some group G, then I could study the Balmer spectrum of compact objects in a homotopy category of G spectra for some fixed group G. And ask, well, first of all, one needs to ask, so what are the thick prime ideals in there? And in fact, they are kind of analogous. So these ones are indexed by a prime P on the level n. And these ones are indexed by a prime P level n and subgroups of G. And they are precisely those X in compact objects of G equivariant stable homotopy categories such that now is it an n or an n plus 1? N or an n minus 1 doesn't really matter because talking about all of them together, such that you apply geometric fixed points, which we now know what that is, to your G spectrum X. Once you've applied fixed point, you just have a spectrum. Once you just have a spectrum, you can apply a homology theory of spectra rather than G spectra. So these are the Balmer primes in the equivariant case. Then, of course, the question is, can one draw pictures? Yeah, so in order to try and draw pictures, people have to figure out for which H's and P's and N's these would be included in one another. And if you also have the subgroups to deal with, then yeah, let's just say finite for now. I think probably, but for what I'm going to say next, it's just for finite, so might as well. So if I have a finite group and K and H to be P groups, then one knows that this one, and there is an S, I could specify that if you really wanted to. So S is the P logarithm, so the exponent of how often the K is included in the H, the exponent of that. So that is included in here. And one could, for example, if you know that, then that kind of helps you to draw some of the edges in your pictures. But to draw the complete picture, you need to ask yourself, what is, oh, that is so clever. What is the minimal I for which this one is included in that one? Just because this one is true, doesn't mean that that is the only shift for which this one is true. So people are trying to find the minimal I for which you can draw an edge in your picture. And I've just picked up a random piece of chalk, which is nice because that one would also be called the nth blue shift. And people are trying to figure those out. And for some groups, they have actually figured them out. And if I was the sort of person who could be bothered to prepare slides, I could now say, can I please have a slide of a picture with lots of lines in? And there it is. But I could also just tell you to go and look at one of Balmer's papers, in which for some small groups, one could make these concrete for all the subgroups that you want, and then draw very impressive pictures like that. It's the nth blue shift. So, that's good. So now for something slightly different. So going back to the early noughties, which will then make us come back to actually this week when this paper got published. So the chromatic square is still there, but that is just a square, a pullback square on objects. What people would really like to have, and people have done, is wanting some kind of version of a chromatic square of the respective categories. So that is quite a hardcore thing to ask for, but so that has been done by Scott Balchin and John Greenlees and various other co-authors. As in, I think this paper is just the two of them, but there's lots of variants of this with a varying set of other people. So as a model category, that of course I can just consider to be modules over the local sphere because it's a smashing localization. And then this is Quillen equivalent to this diagram of model categories with the so-called homotopy limit model structure. So if you plug in the sphere, you of course get sphere, 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 but you can also just then put modules behind all of that. Have to erase. I can tell you what that means in a sec. So an object in here is what? So if you have a diagram like so, with Quillen functors, then objects in here are given by an object here, and a natural transformation with the image in here and the image in here. And the co-fiber objects are precisely those which coincide here. But you don't really need to know what that is. If you don't, then nothing I can say in 5 minutes will explain it to you. And if you already do, then you don't need to hear. So let's just try and tell you how to think about this. So really, the one thing to take away from it, if you've never seen anything like this before, is that one can try and do these for actual categories. So all objects simultaneously in some sense, simultaneously and in a homotopically meaningful way, and not just, okay, I have one square for each object. And well, the thing is, the thing to note is where the troubles really begin and not even end. This one is absolutely not the same as Kn local spectra, because just in in the algebraic sense, modules over the complete unit are not necessarily the same as the completion of the object. So if you want to complete an object, it's not always, it hardly ever works to just say, oh, I just tensor it with the complete unit, as we have seen, I think, this very morning. So this one is always trouble. This one is nice, but here, don't even go there. So this is part of Scott's and John's general machinery, where if you have a model category C, a stable monoidal model category C, and you take a set of compact objects, then you can always kind of, there are ways to recover your entire C from, well, you can cook up a nice and smashing localization functor belonging to that set K. You can also come up with a completion functor, lambda K, and here there's going to be something along the lines of here be monsters, something that glues them together. So the philosophy is that for any pair C and K, you can split C up into a local and the complete part and the gluing part. And of course, depending on what you would like to do, you'd better pick your K cleverly. Yeah, there is in fact a version where you can use K and local spectra rather than what I wrote here, but that would use infinity categories rather than model categories, and only Neil knows about that. So, to join that with something from 16 years ago, and even further. So here on this board, I had this example of this tensor-triangulated equivalence between Kn module spectra and graded Kn star modules. And I said that this was not induced by Aquilon equivalence. So in general, if I have C and D stable model categories, and I have Aquilon adjunction I, then I get a equivalence of triangulated categories between the respective homotopy categories. But the converse is not, absolutely not a given, as we've seen earlier with Kn module spectra and Kn star modules. So the question is, are there any model categories whose homotopy theory is entirely determined by the triangulated structure of the homotopy category alone? And if that happens, it's very special. So the theorem by Schwede, I think 20 years now, I think. Well, 3 versions of that have been flying around before then, but I think that's when it kind of was all complete and published. So if I have a triangulated equivalence between a stable homotopy category and something else. Let's call it D, because I also called the right one D. Then this other mysterious D also has to be Quillen equivalent to spectra. So he started with that because he wanted to show that at the end of the 90s, there were all these different categories of structured spectra, and he just wanted to show that in order to compare them, you didn't just have to compare each new upcoming kind of spectra to others. If they all realized a stable homotopy category, they would be rigid. They would be Quillen equivalent to a standard model of spectra of your choice automatically. So he called that the stable homotopy category is rigid. And now I really wish that Henning had not mentioned what a rigid triangulated category is, because it has absolutely nothing to do with that. I think it's an awful name. I think you should have named it formal, because it's a bit like, like when you can recover the data of a chain complex just from its homology. I would have thought that formal is a better name, but I mean, if it's published in the annals, I can't really go and overwrite that, can I? So, so my thesis from 2007 said that for p equals 2, the K-local stable homotopy category is rigid. But there is, even from the 90s, that for odd primes, it isn't. So the K-local stable homotopy category at different primes has very different behavior. And well, what does that have to do with any of what I just said? And I promised research from, not this week, from last week. It doesn't get any more current than that, does it? So now look at this and look at the all chromatic square. And as I found out, much to the disappointment, the bitter disappointment of my supervisor, who didn't hide how disappointing he found that, if you try any other LNs, forget about it. It's horrific. You can't say anything. This one is calculational. It uses the fact that the telescope conjecture is true at n equals 1. So for higher n's, you just can't. But can we at least say something about the relationship between the uniqueness of the different layers to each other? So last time, that was a pre-theorem. Now it's an actual theorem. So we have the equivalence of the following statements. En local spectra is rigid if and only if, not just rigid, unitarily TT rigid, which means just a version like that, but also having to preserve monoidal structure and unit. That one is true if and only if it was true for all the layers. And that is also equivalent to saying the one below is unitary TT rigid, and the layer between the two is unitary TT rigid. So we only know there is this kind of special uniqueness for n equals 1, but if we knew that that one was rigid and that one was rigid, then so would be the next level up. So also this kind of uniqueness question, which is very difficult, and well, I mean, it's not really doable to actually prove it by hand, but at least we can say that in theory, we could pull it up from its layers. And yeah, I mean, there it is. That is at least the latest that I know. And I think that's a good time to stop. And thank you very much for bearing with me for the last 5 hours of this. It was an absolute pleasure, and I will do it again anytime. Thanks.